You know, when engineers look at a materials data sheet, they see these neat little numbers for things like strength and hardness, and we rely on those to build, well, everything, from our bridges to our airplanes. But today, we're going to dig into what a number on a spec sheet really tells us, and why sometimes it can be dangerously misleading. So let's just kick things off with a big question, one that really challenges a core assumption in engineering. We have this tendency to think of a metal's strength as this fixed, constant property, kind of like its color or how much it weighs. But what if that's just not true?
You see, we often boil down our entire understanding of a material's strength to one single value, like yield strength. It's basically the point of no return, where a material stops stretching and bouncing back and starts to permanently bend. It's an absolutely critical number for sure, but it is just the first chapter in a much deeper and way more interesting story.
All right, so let's really get into it. To see why that single number can be so tricky, we're going to look at how the exact same piece of steel can be transformed into two completely different materials. Okay, so imagine we've got a specific type of steel. The recipe, the chemical composition is totally fixed. We haven't added anything, we haven't taken anything away. The only thing we are going to change is how we treat it.
First up, we take the steel, we heat it up, and then we let it cool down really slowly. What do we get? A respectable yield strength of about 420 megapascals. That's our baseline.
Now let's take that exact same steel, but instead of that slow cool down, we quench it. We plunge it into a liquid to cool it off extremely fast. And wow, look at that. The yield strength just skyrockets to over 1150 megapascals. That is nearly a 200% increase in strength from the exact same starting material. All we did was change the cooling.
But, and this is a huge but, that massive gain in strength doesn't come for free. There's always a trade-off. As the quote here says, whenever you make a metal stronger, you almost always lose some ductility. That's its ability to bend and deform without just snapping in half.
And this chart illustrates that trade-off perfectly. This is for a high-strength steel. See how, as engineers gently reheat that super strong quenched steel to higher and higher temperatures, the strength actually goes down? Why on earth would they do that? Well, they're intentionally trading some of that raw strength to get ductility back, making the material tougher and a lot more reliable for real-world use.
So that leads to the big question, right? Why? How can a simple change in cooling have such a ridiculously dramatic effect? Well, to figure that out, we've got to look deep inside the metal, at its microstructure.
The secret is right here, in the steel's internal architecture. On the left, with slow cooling, the atoms have time to arrange themselves into these nice, soft, kind of rounded crystal structures. But on the right, when you quench it, you freeze the atoms in place, creating this highly stressed, needle-like structure called martensite. That martensite is what makes the steel incredibly strong, but it's also what makes it brittle. Same recipe, totally different internal machine.
A great way to think about this is to picture a complex, microscopic machine inside the metal. The processing, all that heating and cooling, is what builds this internal machine. And different processing builds a totally different machine with completely different performance, even if they're made from the very same parts.
And this is where it gets really critical. Because just trusting that one single number from a datasheet isn't just a little misleading. It can be downright dangerous. So check this out. We have two steels here, steel A and steel B. In a standard lab test, they look identical. Both have a tensile strength of about 1 gigapascal. You'd think they're interchangeable. But watch what happens when we introduce a tiny notch, something you see all the time in real parts. Steel A fails early. It's a catastrophic failure. But steel B, it can stretch over 60% more before it finally gives way.
So what's going on? Why the huge difference? It's because that simple tensile test is just an average. It doesn't capture how those unique internal microstructures handle stress when it's concentrated at a defect, like a sharp corner or a notch. One microstructure is tough enough to stop a tiny crack from growing, while the other one just lets it run wild.
So after all that, what's the big takeaway? How should we be thinking about a material's properties if the numbers on the page don't tell the whole story?
This quote, right here, really sums up a powerful shift in thinking. A property isn't something a material just has, like it's a possession. It's actually a description of how that material responds to a very specific set of conditions. Its history, the temperature, how fast you pull on it. You change the conditions, you change the response.
So really, it all comes down to context. The numbers we see aren't fixed constants. They are the result of the material's entire life story. Its chemical makeup, sure, but just as important is its processing history. That history built a unique internal microstructure, and it's that microstructure that truly dictates how a part is going to perform out there in the real world.
And that leaves us with one final, crucial thought. The next time you see a material strength listed as a single number, don't just ask what the number is, ask how it got there. Because understanding the story behind that number, that's where true engineering really begins.